Welcome back, everyone. In the last video, we saw the idea of a finite set. We saw two videos where we saw examples of finite sets. In this video, we'll see our first example of an infinite set, and it's going to be one that really permeates all of data science, the idea of the real number line. In this video, we're going to first tell you what is the real number line, this funny symbol blackboard R. We're going to go over simple concepts you've undoubtedly seen before, but we want to put into a rigorous framework like positive numbers, non-negative numbers, non-positive numbers, and we'll talk about a little thing called absolute value. It should be a short video. Okay, so first let's meet the real number line. What we do is we draw a line. I refuse to ever draw it straight. Suppose this is a real number line. It goes all the way on the extreme right, positive infinity, and the extreme left, negative infinity. And you want to think of this as representing an infinite set. That infinite set is going to be called R, which we usually write this sort of blackboard R symbol. This is equal to the real numbers. Somehow the idea is that every single dot along this line represents a real number. There's a ridiculously large infinite number of them, and we're going to think about what some of those are. First, let's mark some we know. So usually somewhere in the middle we put 0. And then we sort of make tick marks for whole numbers. So here's 1, here's 2, here's 3, here's 4, here's 5, on forever. Here's -1, here's -2, here's -3, on forever. If we're being careful, we try to make the length of each of these little sticks the same. Okay, so what I just wrote down are whole numbers, what are often called integers. So a subset, which we often call blackboard Z, consists of just the integers. This is ... -3, -2, -1, 0, 1, on forever. Okay, not every single number on the real number line is an integer. In fact, most of them aren't. Suppose we blew up this little stick between 1 and 2. Let's just take it out here and blow it up, just so we can see it better. So here's 1 at one end, here's 2 at the other end. Let's just draw that. The only thing you really need to know here, without getting into any details, is that every single thing between 1 and 2 is also a real number. Same between 2 and 3, same between 3 and 4, and that there's a ridiculously large infinite number of numbers between 1 and 2. How do you make them all? Sort of here's a recipe. Take 1, put a dot, put any string of whole numbers you want afterwards. So for example, 1.1 is in there. There it is, about there, 1.1, about 1/10 of the way. So is 1.4. There it is. So is 1.1538, which might be about there. And in fact, anything that you do, whether you continue on finitely or really infinitely, is a real number. That's the case for any subinterval in here. So if I take this subinterval and I blow it up out here, here's -3, here's -2. Right about there might be -2.5, and so on. So really a real number is any integer, dot, any string of integers you might possibly want. It's a little bit of a nicety which we won't get into, which is that some of these strings of integers terminate, some of them don't. You've probably heard of real numbers like pi. Pi, somehow you've probably seen, is approximately 3.14, 128, so on and so forth. One of the things that goes bump in the night, there are real numbers which are represented as strings of decimals which continue on forever, don't repeat, don't have any pattern. Those are called irrational numbers. We're not really going to think about those here. Really here the take-home message is just a real number is any number along this line, and there are a whole bunch of them. Okay, one of the things we often do as mathematicians is we sort of compartmentalize big sets into smaller and smaller sets and give different categories for what things are. So the first very big division of the real numbers is into positives and negatives. So here's our friend, the real number line again. Here's 0. Anything to this side of 0 we call positive reals, positive real numbers. Anything to this side we say are the negative real numbers. So an example of a positive real number might be 5.3, might be 0.001, Example of a negative real number right here might be negative 11.7. If we include 0, so the positive reals but including 0, we often write the non-negative reals. And if we include 0 on the other side, we often write non-positive reals. Okay, fine. Let's draw that real number line again. Try to get straighter each time. An important thing to realize is that in some sense numbers come in pairs, positive and negative versions of the same number. So here's 0. Suppose I take the number over here as 7.1. It has a friend on the other side called negative 7.1. Just like here you have 10, here you have negative 10. Now notice 7.1 is not equal to minus 7.1. 10 is not equal to minus 10. However, 7.1 and minus 7.1 have one important thing in common, which is that they have the same distance to 0. The distance from here to here is about 7.1, in fact exactly 7.1, and the distance from here to here is 7.1. There's a concept called absolute value. Let's define that. The absolute value of a real number, let's say the real number is x for the definition, which we denote like this, x with a little symbol around it. Notice that it looks exactly like the definition of cardinality of a set, which is unfortunate, is the distance from x to 0. So you want to start at x, you want to walk to 0, and you want to figure out how many units you've walked. We'll notice over here that the absolute value of 7.1 is 7.1, and the absolute value of minus 7.1 is 7.1. Which, by the way, is the same thing as negative 7.1. That's not just a cutesy little formula. We all know that negative times negative equals positive, but it allows us to make a general definition. So let's write down on here. Here's a general rule. For any real number, for any x and r, the following is true. The absolute value of an x can be one of two things. What I'm going to do here is give you what's called a definition by cases. Part of the point of teaching this is not just to give you the formula for the absolute value, but also you're going to see this definition by cases throughout data science. The absolute value of x is equal to plain old x if x is non-negative. But it's equal to negative x if x is negative. Let's check that's true. And while we check this, will sort of show us how to parse the definition by cases. So let's compute the absolute value of 8.7. So according to this definition, 8.7 is our x. It's either going to be 8.7 or negative 8.7. But which case happens? 8.7 is non-negative. So I'm in this case up here. So this is just equal to 8.7. And that's true. Right? If I draw my real number line, here's 0, here's 8.7, that distance is 8.7. Let's check a different one. This shouldn't surprise you, let's check a negative one. So let's check negative 10, the absolute value of negative 10. What should this be, by the way? If here's negative 10, it should be this distance, which is 10. If I go through my definition, negative 10, okay, 10 is negative. Therefore, this formula tells me to take the negative of negative 10. Is equal to negative 10, which lo and behold is equal to 10, which is what I wanted. Okay, that concludes this video where we've learned what the real number line looks like, what it means to be positive, negative, non-negative, and non-positive, and also about absolute values. In the next video, we're going to jump into the idea of inequalities, what it means for one number to be less than another number, less than or equal to another number, and so on, and we'll connect that back to absolute value.